All right, origin. We talked about it. We've hinted at it many times. Let's finally figure out what's going on here, right? This presentation will cover the use of origin in Frame and how you can customize and extend its abstraction. I want to mention this origin thing. I think it's underappreciated and kind of misunderstood because obviously like everyone has in their head like, oh, there's a caller. The caller has an address. Like in Ethereum world, the caller is just an address. But we are actually here with the origin creating a very flexible access control layer for your palettes. It's extremely powerful, extremely extensible, and it turns all of your ideas into modular pieces of this overall runtime system. Okay, I would love to splurge on all the different cool ways we use origin inside of Polkadot, and hopefully I'll cover some of them here, and then if not, we can talk about them in questions. Okay, but origin is cool. It's really cool. So what is an origin? All dispatchable calls have an origin that describes where the call originates from. Again, an extrinsic or dispatchable or a call, whatever you want to call it, is some kind of message from the outside world coming into your blockchain. The origin describes where that thing is coming from. Now, the most obvious origin, again, from the Ethereum world days, is that this is coming from a user with a private key. But what if we were to extend that abstraction? What if you were accepting messages from parachains? What if you're accepting messages from governance bodies? What if you're accepting messages from ephemeral aliens who use some, I don't know, others like that? The origin is a much more, like the idea of something originating from somewhere is a much more extensible thing than a private key. And again, a really great example of why origin exists is in the mindset of things like parachains, in the mindset of things like bridges, in the mindset of things like cross-chain communication, right? A blockchain does not have its own private key, does not necessarily have an address. When you assign an address to something, you're just hacking. You're just hacking some idea on top. An origin is much more flexible, much more directly understood idea of where things are happening, okay? But anyway, we have here a very simple extrinsic, the mark extrinsic, right? You can see here, it ensures signed or root. So we have an origin check. We can accept both a signed origin or a root origin, and the function ends. Again, as you mentioned this, we talked about this already. This function is kind of weird. It inscribes that on the blockchain, but still we have origin checks. Okay? So the default origin, the origin that you all have access to by default because you use Frame system, is this origin here, the raw origin. And that has three variants: a root, a signed, and a none. Okay? I think I talked about each one. Yeah. I guess at a high level, you said already root is the root access. It's like basically whenever someone gets root access, they have access to every single thing in your blockchain. There are root functions in system to upgrade your blockchain, to delete storage, to access storage. Whenever you create root access, they are the blockchain itself, okay? Signed, that makes sense. None, again, we'll talk about none maybe at the end, where there's some kind of unique uses of none. So how is it used? The runtime origin is used by special functions to check where the calls come from. Again, it's very similar to message sender and Solidity, but it's more powerful. There are all these origin checks available to you through Frame system. So all the basic ones: ensure root, ensure signed, ensure none, ensure signed or root. And if any of these combinations don't work for you, you can of course create your own chaining logic to check the origin is whatever you want it to, whatever you expect it to be. So an example here, very simple. We have a signed origin check. This is a function transfer only accepted from a signed user. We take the very first line, take the origin, ensure signed, extract from it the account. Most extrinsics use the signed origin. Here's an example for root origin. Root origin obviously doesn't extract an account ID. There's no account ID for root. It's just root. So here you just take ensure root origin, and again with the question mark, it'll either return an error or it'll succeed, right? Root has access to many functions which can directly modify your blockchain. Assume that root can do anything. So one thing that's cool, right? When you're designing your blockchain, you don't need to think about governance bodies or whatever, or like, designing your palette, you don't need to think about governance bodies or all of the access control layers. If you're building, for example, a multisig palette, and you want to create a function that's like, force add user to multisig, right? You can create that function, have it be a root call, and then know that this function is only accessible by other governance bodies in your palette, right? You're able to expose like back-end calls, back-end features of your palette without having to design all of the things around like, access control, right? So if you have this function, force add user to multi-sig, then if you have sudo on the account, you can access it. If you have governance on the account, you can access it. If you have whatever you want, you can access it, right? So actually think about exposing additional functionality to your block, in your palette for your users, right? Did what I just say make sense? I feel like one more time. Okay. What I'm trying to say is that because root origin is assumed to be able to do anything, you can actually add extrinsics to your blockchain which expect the root origin, which can do crazy things, but could be utilities for helping your blockchain. For example, in a normal smart contract, it would never make sense for you to have a function force add user to multisig, because you never want to have a backdoor where you're adding users to multisig automatically. But you could imagine that somehow in the world of blockchain, this is a useful tool that governance could access. By making a root call, you basically are enabling governance to access it, right? So there's ways you can add additional functionality to your blockchain through the root origin, giving you like an extensible access to like low-level permissions, right? Maybe it fixes up your chain, maybe it deletes a proposal, maybe it does whatever you want, right? That's okay. The non-origin. So here's an example of the non-origin. This was actually in the timestamp palette. I've been ignoring it up until now, but I think now I'm finally have to explain what's going on here. But you can see here there's an ensure none, and it does some stuff. So I think there's more details next, okay? But by the way, non-origin, again, in your entire blockchain experience, if you never use the non-origin, that's normal, okay? But I'll try to explain it here. If it doesn't land, that's okay. So non-origin is usually used to represent extrinsics, which are specifically included by the block author. So when I am the author of a block, I am already putting myself in a privileged position, right? I am building a block. I am doing things in that block. And I can represent I can add a message into this block or add an extrinsic into this block from me, the block author, where I'm the only one who can actually add this extrinsic, and through this non-origin. And then we have additional checking logic which you can include in your palette through this provide inherit. So this idea of a block author adding some information to your blockchain, that's called an inherent. And we have additional checking logic in provide inherit which can help check that this information being added is reasonable. Okay? And there's some little template for it here. And if you want to go look at the timestamp palette, you'll see a more fleshed out example. Another time you can use the non-origin is for an unsigned message. Now, I want to clarify. In general, there is no unsigned messages, okay? Like a signature on the message is a very important part of accepting a message. But when we talk about a signed message, we're talking about a traditionally signed message. So if your blockchain uses, what's the encryption we use? ED25519. A signed message is a payload with a signature of ED25519. But what if your blockchain also wanted to accept messages from Ethereum? That would be a different signature scheme, right? So in this context, we don't expect a standard signed message. We expect an unsigned message where potentially in the payload, there'll be a signature that we then check, right? So again, with this unsigned extrinsic, we have our own validation logic, which bypasses the normal signature flow. And you can then include signatures of other types or of other mechanisms, other cryptography, inside the payload. And then you can have your own validate unsigned logic, which validates that message is there. So again, it doesn't really make sense to accept a message with no origin. It doesn't accept that a no origin message doesn't make sense. If it comes from the block author, that makes sense. If it comes from a user that isn't using your cryptography, but is providing other proof of where it's coming from, that makes sense too. Do you see what I'm saying here? This is just basically a method for you to bypass the standard verification process. And through this, we use this method in the genesis of Polkadot. Polkadot had an ICO where it sold tokens to Ethereum users using Ethereum smart contract. We allowed, and we still allow, if you have your Ethereum private key and you have you bought DOT in the ICO. We stored all of those transactions onto the Polkadot chain, and you can actually sign an Ethereum message, send it to Polkadot, and we'll give you your claims. So in this context, we are supporting Ethereum signed messages using validate unsigned because in the payload, it includes the signature. Okay, let's bring the microphone to the back. It's cool though, right? So again, none is not something normal to use, but it's a tool, it's a powerful tool for you that you have optionality to. What's up?
So in this context, okay, you mentioned ED 25519. So implementation-wise, essentially, if you wanted to do like a verify, then inside this call, you go ahead and call the respective cryptographic library. Is that?
I think that's exactly right. I mean,
yeah.
I think I can even show you. I think it's probably pretty fast. Let me see if I can find it.
Sure, because I mean, I was thinking from an architecture perspective, whether that's where you make the call or if it's like a separate palette that you create for that particular crypto that you're using.
No. So you would obviously import some kind of crate, like the crypto library crate,
the crate,
but you call it directly in the palette.
Oh,
So-
okay.
Yeah. The other question?
Yeah, I have two questions. One is this: when we are using this, then there is a potential spam attack situation, DOS attack situation.
No, right.
How
So
do we, recommendation for avoiding it?
Sure.
Yeah.
So you have to remember that every single blockchain has a spam attack situation. Like, I mean, even there are invalid calls or bad signatures. So when transactions are coming in, what we do is as quickly as possible we validate them. So this validate unsigned logic that when I showed before, it is doing validation at like the transaction pool level before it even gets to the runtime, before it even makes a block. It's happening way sooner. And in that validation logic has to be very small in size, but it has to be enough to validate. So I think your question is great because you're keeping in mind, if I do a lot of work in there, that's bad for my chain. And that's correct. You need to be able to validate things very simply. If validation requires, I have to go read a storage item, call an XCM message, do that, it's not safe. That's not a safe usage, right? It needs to be cheap to validate.
Yeah, and one thing I'm just thinking, like, because Ensure signed is a very flexible framework already, so we can maybe in future get the parameter from the user that, hey, verify me through this signature scheme, and that signature scheme Ensure signed will take and verify using that scheme.
So we actually already support that. Inside of Substrate, we don't use a single signature, we use a multi-signature. So actually, I can show you that too. So let me show you that next. But we actually support multiple signature schemes inside of one blockchain. But if you want to use one that isn't supported directly, then you can use this method.
Oh, you are already brute forcing it.
Yeah, I will show you those two things. So let me quickly take a pause here on this, okay? So here is in Polkadot runtime common. There's this claims palette for claiming your tokens. There's a validate unsigned, and let's see in here. I'm gonna find ensure none. Ensure none. So there's a function called claim. Let's see what it says in the text. Here we go. Make a claim to collect your dots. Unsigned validation. A call to claim is deemed valid if the signature provided matches the expected signed message of an Ethereum signed message. Right? And the address matches the destination account. So if we look at the payload of this thing, we include a signature in the payload. Again, it does not make sense to accept messages without signatures. Signatures are a way for you, again, from all the way back to cryptography days, to ensure that a message is coming from a user, that they cannot say that this message didn't come from me, that it identifies who the user is. You always need signatures or identification when you're accepting messages. But in this context, we have the payload of the signature in the parameter calls. Okay? Then we can do ensure none. But before this code is run, we actually do the unsigned validation, or validate unsigned. Validate unsigned. So this is logic. This is a hook that's happening before. You can see it has a match statement. It matches. If you're calling claim, we have the parameters here, the Ethereum signature in the parameters of that call, and we actually do ETH recover, which is the recovering the address from the signature. So this is very lightweight. This is acceptable computational overhead for a transaction, and now we just supported a brand new signature scheme in our existing blockchain. This happens. It might even happen one or two times during the whole flow, but I think it happens primarily in the transaction pool. I believe the transaction pool is constantly checking, are these transactions valid or not? And there's a bunch of different things, but this is the validation logic here. But if you want a more direct answer, you're gonna have to force me to look in the code, so you can ask me that in Discord, and I can maybe give you more information. But it's happening very lightweight. Yeah, question.
Is this a method that we would use if we wanted to override the SR25519 signature scheme, or how would that work? So, for example, and to give you context, like I want to be able to implement P256R1.
So there's many ways you can do this. So one way you could do that is you could build your blockchain with that scheme in mind. If you don't want to do that, if you already launched a blockchain and it already has these, like imagine that DOT launched and it's been around for like 20 years, and the standards are here, but you want to support this new address format for whatever reason, then you could do something like this. It's just an option. This is one of many options, and I bet you could think of a million other options of ways you could do this, right? But this is one option to bypass a message having to be forced to be signed by your default signature scheme.
Got it. Would it be, I guess, looking into the Frontier palette be the best way to kind of see how they did the entire...
No, Frontier palette actually just implements the Ethereum signatures directly into the substrate, the better way. So again, the reason why we do this in Polkadot is not intending to support Ethereum signatures.
Got it.
But for this exact one call, we want it.
Okay.
Right? What Frontier does is actually the whole substrate stack uses the Ethereum signatures.
Got it. Okay. Thank you.
So then let me show you one more thing real quick, okay? Again, these are very much advanced things. These are not things you expect you to use, but you're asking the questions. I want to show you the cool things that are happening here. The last thing is multi-signature. So enum multi-signature. Here we go. So we already use this object in all of your default runtimes. So if I go into your project, let's actually go into your project. So this is the Hong Kong assignment. If I search multi-signature, signature. Inside of your runtime, the signature scheme we use in your runtime is the multi-signature. So all of your blockchains already support 3 schemes. And our multi-signature inside Polkadot SDK is ED25509, SR25509, I'll bring it up, and ECDSA, which is the Ethereum, right? So you already support all these themes. You could actually, I guess at this point send, what is ECDSA? That is Ethereum, right?
Yeah, ED25519.
Yeah.
And SCCP 251K1.
Yeah, exactly. So yeah, this is Ethereum. So you could already send an Ethereum signed message to your blockchain, and it should figure it out. Now there might be some type compatibility issues. Like it might be, again, the Ethereum addresses are 20 bytes. The Polkadot addresses are 32 bytes. So maybe there's some finicky here, but the fact is that this is basically the low-level implementation of this scheme. And I do think that this is one of the places where if there is if you were to create an RFC for the fellowship to introduce a new line item here, you could actually introduce new schemes to Polkadot. Wow. Or at least to the substrate ecosystem.
Okay.
Sure.
Yeah.
Let's go here first.
So users, without specifying which signature scheme user has used to sign the message, substrate system checks one by one. I
guess so. I mean, let's look real quick.
Okay.
I mean, somewhere we're doing some kind of I guess we match. So there must be some bytes that tell us which one we're using. But basically, you look at this, there's like checks. Like it tries to check each one and tries to convert it. Oh, look at this. If you use EDCSA, we take the address, which is 20 bytes, we hash it and make it a 32-byte address. Look at that. That's right there. So for the other ones, we can directly get the address because they're 32 bytes. For ECDSA, we do some Blake 256. So there you go. That's how we did it.
Nice. Thank you.
It's just in the code. Dude, I don't know who uses this. Maybe I don't think even Moon may use it at this level, but it. No, you need to speak into the mic. I can't hear you.
Yeah, you take the mic.
Like we're talking about the initial Polkadot to Ethereum thing, right?
You're still mumbling.
Right. We're talking about the initial Polkadot to Ethereum.
No, so you might be confusing. What I showed you before was the unsigned stuff.
Yeah.
I'm showing you here the signature stuff. Okay. So a signed message to Polkadot, a normal signed message, already supports 3 different cryptos.
Okay.
And we by default support this.
Okay.
But obviously the address that gets generated from a Ethereum message does not match the address you would expect from Ethereum.
Okay. But about the unsigned one, like you
Okay, about the
basically
unsigned one.
You basically had like a list of all um, the accounts that you wanted to issue the tokens to.
Right.
Yeah. So we just matched it to.
Yes, exactly. So there was some storage in the blockchain which told me this address on Ethereum had this much dot, and we give it to the dot.
Okay.
Okay. Yeah. Last question. Let's not get too hot on this.
Yeah, I'm just curious from, I guess, the way the fellowship works, or from an engineer perspective. Would there be a lot of complexities to introducing a new, cryptographic signature?
No, because that's the thing that like for example, even if you add this new signature here, inside of the Polkadot world, everyone in all the wallets will use ED25509. That's the default. And as long as you can take a signature and you can convert it into a unique 32-byte address, then it looks the same from the pallet perspective, right? If pallet only expects 32 bytes, the signature verification process that gets from a private key to public key is like opaque to the runtime, right?
Yeah, I guess the wallet libraries or the Polkadot JS will need to support this additional.
Exactly.
Yeah,
That's
the only
outside
thing.
of the runtime problem.
Okay, got it.
Right.
Thanks.
Yeah. What I would be worried about, which seems very unlikely, is that somehow that two very, very cleverly selected signature schemes have collisions. Like if somehow you were trying to be really malicious, you create, scheme A, scheme B, and they collide with each other somehow. That would be bad. But
Right. There's a thing where Satoshi didn't want to use P256 R1 because that's the NSA curve.
yeah, exactly. So these are the kinds of things where I prevent. But other than that, like from the runtime perspective, we give you 32 bytes. This is a unique address, and how we get that 32 bytes, we handle that on the client side through signature verification, through hashing, through whatever we need to do to be able to verify things. Okay.
Got it. Thank you.
Okay. So I want to. We're stepping away now from the unsigned thing. Unsigned origin, very cool, very powerful. You're never going to use it, practically speaking. But it's there, right? We use it, so it exists. Okay. Custom origins. So I showed you now the default origins. Root, signed, none. What if I told you you can actually even make your own custom origins in your palettes? This is where things like parachain origins come in. That's where things like governance origins come in. You can actually make your own origins and implement them in the runtime. That's the powerful, extensible part of our framework. So, inside of your palette, you are able to introduce a new struct called origin with this palette origin macro on top. Okay? Then you're able to define a raw origin with whatever variants you want inside of it. So if you want to create an origin, for example, in voting that has members or member, you can do that. So let me explain what this one is. So this is a palette which allows the collective to vote. So there was like 12 people in a collective, and they are making votes on behalf of things. So imagine there's a new vote. We want to upgrade the runtime, and that users in the collective, they vote. Let's say that there's 9 users. 5 of them said yes. 4 of them said no. Using logic in the runtime, I'm able to construct an origin which says members 5 out of 9 approve this origin call. And then I'm able to create on the other side a runtime upgrade which says if the origin is at least majority, do the upgrade. So this member origin reflects now this idea of majority, and we can do checks to support it. That makes sense here? I'm able to take and aggregate a bunch of people voting, turn it into a single origin, which is custom, which conveys ideas, which can then be checked later, and then used to control the access to call the functions. I want to show an example more, but that's the high-level idea. You can make custom origin. This is very, very powerful. So an example of this is the parachain origin, right? So inside of the Polkadot palettes, we have created a custom origin called parachain. And the parachain origin, of course, instead of conveying an account ID, conveys a parachain ID. And then when you write your runtime functions, which are connecting to parachains, you can store an access control layer which uses the information of which parachain is talking to you, right? And then, of course, a lot of this origin stuff is being used through redispatching. So normally, like most calls normally come from users. But again, as I mentioned, with things like the membership origin, you could actually accumulate user calls and then redispatch a call with the origin of your control. So in this context, this is the pseudo palette. We talked about that yesterday. Yesterday? 2 days ago? I don't remember. This is the pseudo palette. And you're actually able to take a signed message from a user, do some logic on it, and then redispatch a call using a new origin. In this case, the root origin. But you could also dispatch it with whatever origin that's available inside of your runtime, right? You're able to actually dispatch a call, and then this call will check that origin being legit or not, right? So this call to do an upgrade, whatever, let's say the call is an upgrade, only supports root, but the call starts with the user, and we redispatch it. So this is the kind of logic that you're going to write when you're doing the multisig, when you're doing, remind me all the projects. What's the other one? There's one more. The feeless transaction is going to do this, maybe. A bunch of them. If there might be a time where you want to, or even the voting, the quadratic voting, if you get to the extra part, you will actually redispatch a call, right? Right here. Yeah, pseudo palette is a palette that allows a signed origin to elevate itself to a root origin. That's the power of origins here. So we're able to have this amazing access control layer. So let's look more again at the collective palette. So that was already the example I given about membership, right? So the collective palette has this origin definition with members. And then in the collective palette, we have some logic. Do approve proposal, right? And this logic goes in and says, well, this is the number of seats in the whole thing. This is the number of yes votes. Let's create an origin with the number of yes votes, comma seats, right? And let's dispatch the proposal with this origin. Then it's up to this call to check if it passes the criteria. So it could be that the yes votes is 5, the seats is 9, but this call proposal expects 9 out of 9. In that case, it would fail. Or it's configured for 4 out of 9. In that case, it would pass, right? But we're able to construct an origin which just conveys some idea, some value. Let me see one more slide. And you're also able to write custom origin checks. So you make these custom origins. You're also able to, in your palette, create custom origin checks, which can then be used and configured in your runtime, right? So there's this trait called ensure origin, which you can implement and with whatever logic you want on top of your custom origin types. And then in the runtime, where all custom origins are known, you can use them. I will show you an example of that maybe in the code. Okay, here's an example. The alliance palette. So this is obviously, what am I looking at here? This is a configuration of a palette where there are multiple different calls where we want the runtime developer to be able to control which origin can call it. I think a similar example to this was the NFT palette. Remember we had an NFT palette where they had these custom origins for like creating collections or deleting collections, whatever, that kind of stuff. So inside of your palette, you might have a call for some admin operations, for some membership manager operations, for some announcement operations, right? There might be different extrinsics, right, that are gated by these different origins. Now, you do not want to define who has access to these calls. You want to be able to configure, let the runtime configure that access. So what you do is you create these custom origins in your config. They all implement ensure origin trait, right? And then you use them inside of your extrinsic. So instead of doing ensure signed, you can do T, admin origin, ensure origin, origin. Again, we don't know what this logic is yet. This logic is generic, right? We're doing generic runtime. But then, in your runtime, you can go ahead and actually define what the origins are defined as. So in this case, the admin origin is root. Or it is ensure proportion at least 1 of 1. So in this context, the admin origin can be called by root or can be called by a total majority, 100% of the alliance collective. The announcement origin, which is a lower priority thing, can also be called by root, why not? But only requires 1/3 majority of the alliance. Ensure proportion more than this. So you can see here, I created a palette with a bunch of different extrinsics. I have different ideas of the roles, the access control roles in my palette, and I'm allowing the runtime developer to fully configure what those things are. Okay, yeah, I think now is the right time for a question. Okay, so we had one here first. Can you get the microphone? Okay, he got the mic before you. So
I'm a bit confused how the dispatch call will happen with this origin, like in the end. So like
right,
someone
okay.
is calling this, and then
I think I can answer your question. You agree that you have a general idea of generics, right? Generics are able to, you define a trait, and someone else implements that trait.
yeah,
So here I've defined a type which has a trait ensure origin. And this ensure origin is this trait which has a function which is called ensure origin.
yes,
We can use this type and we can use this function in my code. But I don't know yet what this logic is doing, right? Because it's generic. This is just someone else will implement this function for me. And someone else will return to me true or false. Right?
yeah,
And then only in the runtime, when we're actually configuring all the runtime stuff, this magic code here, this behind the scenes, is doing logic, which actually is telling them whether it should pass or fail. And then, so when this extrinsic is called, you hit this line of code, and then it will actually execute the logic defined in the runtime to ensure the origin. If it passes, then the rest of the code is executed. Does that answer your question?
it is easier with when it's like a root. So like for example, it's checking if this account ID is one of these account IDs, but like this collective and
Right.
counts and stuff is.
I think that I can give you a basic answer now, but a better answer will be unveiled when you learn about the outer origin. Like imagine this. Imagine there is a type. Ignore the other stuff, right? So that's just my little area here. Imagine there's a type enum runtime origins, and here there is like default origins, and here there is. Is that the way you do enums? I don't know. Okay. Here there is root, signed, and none. And then here there is parachains. And then here there is member, or like collective. Members, A of B, member, A. So here, the origin that we expect in the runtime supports all of these variants. And the origin check, like ensure root, is just checking this runtime origin matches this variant. Or ensure collective, is it checking that this thing passes this test. So it's just we're matching on an enum. All of the ensure origin checks, it's not actually verifying signatures, it's not actually doing anything, it's just doing an enum check plus maybe some logic. Okay.
My question is that it's not clear how these calls are made from outside. I mean, is there any way for someone to fake these origins from outside your runtime?
No. And this maybe me calling it outside is wrong. An extrinsic comes from the outside. An extrinsic supports signed messages. These kinds of origins cannot be constructed from the outside. You can only, from a message from the outside, can only construct a signed message. From inside of your runtime, you can construct these other origins. And you are in full control over the logic that creates these origins. So a user can only create a signed message.
So a message that comes from a parachain is considered, it's not considered an extrinsic, right?
Okay. No, it is considered extrinsic, and it is considered a parachain. But the relay chain, instead of looking at the signature of something for a parachain, parachains have properties which are uniquely identifiable. For example, the genesis hash, right? So when I get a block from a parachain, I know where it's coming from, and the messages inside that block are the parachain block. But is it called an extrinsic? It's like more like a philosophical question. I think technically it is an extrinsic because it comes from outside the blockchain. But yeah.
But there's no way for someone to like
fake it. There's no way to fake
fake
it.
this message
No, because
and
the
make
only
it callable. Like
the only pipeline where we generate a para ID, again, all these origins, they are controlled by your runtime, right? So you are the one who defines the pipeline for generating an ID. The only way to generate a parachain ID in Polkadot is through the pipeline of importing parachain blocks. So there's no we don't extrinsic from a user doesn't even touch this code.
And the same goes for collectives, for example.
Yeah, but yeah, that's correct. But you could create an extrinsic, right? Which is like user to parachain ID, and then you could just you could create fn user to para ID, which is an origin, right? And the ID that you want, para ID, which is some like ID, and then you could do let user equals ensure signed origin, and then if the some check, and then sorry, I should go scroll up, and then you have a call. Oh, there should be a call. Dot dispatch origin para ID. I mean, you could write this function. That's on you, man. That's like, I mean, it's possible, but it's not that this guy was able to generate this origin by hacking your code. You wrote the code, and all of the logic around generating all the origins is code that you control. So it's on you. Again, this is the same thing with that. Like, there's no magic involved in blockchains. If there's a way for a user to do something, it's because you programmed it. Right? Like, yeah. Any other questions here on this?
So yeah, going back from your last comment, where essentially it's you have the extrinsic, and the extrinsic says the kind of the message, and then internally the origin. I'm just trying to wrap my head around if, following up this question in terms of like oracles. I guess the way that I see what happened is that the quote unquote oracle, will go ahead and do an extrinsic, and then internally perhaps there's governance that says we're approving this message from particular address, and then something would happen with the origin, right? Is that kind of like one implementation?
Yeah, I mean, you could, for example, in a blockchain, you could have a set of addresses which are whitelisted as Oracle addresses.
Yeah.
And they have the permission to make a signed message, go through this palette, and then turn the message to an Oracle message.
Yeah.
And then you could have like a data receiver palette which only accepts data from Oracle origins. So this would be, and then you would
Nice.
use this Oracle upgrade palette, like the one that turns account to Oracle, to control the set of current oracles. So this is
Sweet.
exactly like how you would design a flexible system. You have like a palette which controls the oracles, and you have another palette which accepts data, but doesn't actually know how the oracles are being selected, right? It's two separate palettes.
Yeah. And one quick follow-up question. In terms of that, I guess, how would it work for oracles publishing data? Would it be that? Because currently with events, right, you're saying that we can't query events and we can't save particular data. Is it? Maybe we talk offline about this, but
Yeah, I think you're going
Yeah.
too specific.
all right, thanks.
Yeah. Okay. We're almost done here. So we talked that. So last, fees. So fees are usually handled on a blockchain by some palette, like the transaction payment palette. However, if there is no signed origin, you can't really take a fee, right? The entire fee system depends on me knowing the address where I should take the fee from, right? So if you use the none origin, if you use the root origin, if you use the membership origin, the parachain origin, there is no fees happening, right? Right. So what I say, like, in your extrinsics today, you're not actually manually doing fees, but something in the background is handling the fees, right? When you accept a none origin or a root origin call, there are no fees being taken from that message, right? So it doesn't make sense, right? You can, of course, figure out some way to do fees, but it's all manual. But basically, the pipeline for taking fees only applies to ensure signed messages. Okay? Questions? Any more questions beyond that? Yeah, please.
I have more like naive question regarding origin of collective, like how it works. Because in blockchain, every node it submits it.
I think
Extrinsics, right?
I think you might be suggesting, let's go spend a little minute and we'll look at Polkadot and we can see some of the configurations.
Okay.
Yeah, sounds good. Okay. So let's look at Polkadot. Runtimes. Okay. So who here is familiar by hand with the different tracks on Treasury? There's like a big payer, small payer, big tipper, small tipper, etc. This is all using origins. I think that's a good place to start looking at stuff. So imagine that, and this is how the Treasury palette works, or kind of. The Treasury has a lot of money in it. There are voting systems to determine where the money should go. But don't you agree that if we ask the Treasury to spend $10, it's a lot less important than if we ask the Treasury to spend $10 million? The level of requirement needed to spend 10 versus $10 million is totally different. So why don't we use origins to say we need this much vote to pass for $10 to $100, this much vote to pass for $100 to $1,000, this much vote to pass for that, and that's exactly where we get these different tracks from, right? And so we're able to create a completely very flexible payment system using different origins, and then have it so that a voting system, like when I vote in OpenGov, that it either requires everyone to vote yes, or 10% to vote yes, or 30% to vote yes, and it controls how much you can pay, right? So some combination of the two work together to actually return the outcome. So let's look at what that looks like. By the way, I'm not actually super familiar with that code, but I think I know that's how that works. So let's hope. Governance. An origin which governance can control, which can adjust the staking parameters. There's a fellowship admin. There's an origin which can administrate the fellowship on the blockchain. There is a small tipper, big tipper, small spender, medium spender, big spender. They're all different origins allowing different levels of access to things. These are all customly defined origins, okay? And then you can imagine that if these origins exist, that we can write some logic on how that origin will be created. For example, for big spender, in an open governance system, we need at least 50% of token holders to vote yes. Like that, you can imagine that logic exists somewhere. I don't want to really show it because that's what all this curve stuff is. Like all this curve and this decision stuff, you can see like, you know, the name, there's a decision deposit, a period, like all of this is very configurable. But you can imagine you could write some logic because you're a programmer, right? So now we have these origins. We have some logic which will generate the origin depending on whatever you want to do. Where is this then configured? So let's go look at fellowship admin. So somewhere, I'm expecting to see fellowship admin integrated in the runtime. In the configuration. Here we go. Fellowship admin body ID. Oh, that's not exactly what I was looking for. Let's see. Oh, where was I? Let me search this. Fellowship admin. That looks like it was it, actually. So here, there's this fellowship admin to plurality, which is some kind of origin wrapper around the fellowship admin origin. You know, again, there's lots of abstractions here. I'm trying to hide all the nitty details, but imagine this is that same origin. And somewhere, this fellowship admin, oh, but this is XCM. Wait, give me one second. I want to look for the runtime should have this configuration. Params origin. Ah, this looks better. This looks better to me. This is a palette core fellowship. This is the config of that palette implemented for some runtime. You should all be familiar-ish with this, right? So this is where we're concretely defining a configuration for a palette. And somewhere in this configuration, there is this params origin, which is configurable. Again, somehow this is configurable in the palette designed. And wherever this stuff is using this fellowship admin body ID or origin or whatever, right? That's the high level idea, right? That you can imagine we have generated some origin, we define some custom origin, we can have some logic to generate the origin, and ultimately we configure that origin in some custom palette configuration. Those three pieces make sense? Again, that's what my slides were. My slides were you define an origin, you configure it, you use it. Does this make sense at a high level? Again, I don't know. This is an advanced topic because it's using lots of pieces here. But the idea is, it takes only a few steps as a palette developer to turn a simple palette which accepts only ensure signed into a very configurable palette which can accept many kinds of origins configured by the runtime developer, which can be controlled by governance bodies, by parachains, by whatever. Like all of that is just simple levels of abstraction you can add to your blockchain. And with all of these tools, you're able to create very modular and extensible ecosystems. Right? Any other questions about origins? Okay, then let's take until 12:15.